Right. Now, fellas, now we had the last MCQ of the chemical calculation in 2004. Now, let's jog into the 43rd MCQ. Right. So, this is actually a statement question. So, it's actually about the area which comes under chemical equilibria. So, it's actually ionic equilibria. Ionic equilibria. So, here they are discussing about the ionic equilibria. And let's see what are the statements that they are going to say. So consider a sample of pure liquid water at a temperature T. Right? Now they are asking to consider a pure liquid sample. So pure liquid water sample. In pure liquid water, you should know that there is no any ions that is present in the usual water. For example, if you take normal tap water, you have calcium, potassium, bicarbonates, some amount of lead, maybe cadmium, maybe depends on the type of water that we use. It can be the hard water or soft water. It depends according to type of ion. But in the case of pure water, there you cannot have any type of ions in it. Only H2O will be there in it, right? So, but according to the ionic equilibria, you know there is only water, liquid, right? But we know that there is an equilibrium which is present between the water molecules. Between the water molecules, we have an ionic equilibrium. So when two water molecules undergo partial reaction, giving H3O plus aqueous in the medium plus OH minus aqueous in the medium, right? You can write in this way, or you can just raise this one and just write two water molecules, right? This is also correct. 2H2O liquid, right, undergoes partial reaction giving H3O plus aqueous, right, and OH minus aqueous, no harm. You can write this also. One water molecule undergoes partial reaction giving H plus aqueous and OH minus aqueous. Any of the above is correct, right? Any of the above is correct. No need to fear about it, right? This is the equilibria that is here within the pure liquid water sample. There is no any ions present in it. Okay. Now let's see. So it is present at a room temperature T. We don't know what is the temperature. It can be room temperature or it can be above the room temperature or below the room temperature. Doesn't matter. Right? So at a temperature T, where the ionic product of water Kw, ionic product Kw. So ionic product means they're saying Kw, right? Kw is equal to 1 into 10 to the power minus 12 mole square decimeter minus 6. 1 into 10 to the power minus 12 mole square decimeter minus 6. What does this mean? What does this Kw mean? So Kw, in a sense, we know that it is the ionic product of the concentration of H plus ion in the aqueous medium plus into the OH minus concentration in the aqueous medium. According to the solution that they have given, we have only water. So therefore, you're going to have H plus aqueous from water and OH minus aqueous in water, which has been released partially due to the dissociation of water molecules. So therefore, you will be having the ionic product H3O plus aqueous and OH minus aqueous, right? OH minus aqueous. So this is the thing that they have said. Okay, so which of the following statements about the above sample of water is true? So first statement is the pH is 6. Okay, now they're saying pH is 6. Be careful. Now they're saying pH is 6. Okay, you know, for statement A, pH is equal to minus log 10 H3O plus aqueous over 1 mole decimeter minus 3. That is why pH doesn't have any unit, right? 1 mole decimeter minus 3. So you need the H3O plus aqueous here. Now once you write the ionic product of pure water, what will happen is, here you are going to have the same ratio. Why? Because once this amount of X that is formed here will be equally distributed to the OH minus. Let's say if X mole has been dissociated, right? You will get the X mole here, right? X by 2, and here you will get X by 2. Why? Here you have 2 moles. But here we don't consider the moles of water here, because here water is in liquid state. So which means it is in its pure form. So you can't use a pure substance over here. It's smaller concentration there. So what we'll be using is the same amount of concentration that is there for H3O plus and OH minus aqueous. So what I'm going to do is, I will write the concentration of OH minus with respect to H3O plus aqueous. You will get H3O plus the whole thing square. So H3O plus aqueous the whole thing square is equal to Kw. So what the Kw they have given? So 1 into 10 to the power minus 12 moles square decimeter minus 6. So if you bring this square to the other side, you get square root. So final answer will be H3O plus aqueous is equal to 1 into 10 to the power minus 6 mole decimeter minus 3. Right? Now you have this much of concentration of H3O plus. If you substitute here, you will get pH is equal to minus log 10 1 into 10 to the power minus 6 mole decimeter minus 3 over 1 mole decimeter minus 3. So mole decimeter minus 3 will be cancelled. You can bring this fellow to the front. So what will happen is, you will get pH is equal to 6. So therefore statement A is absolutely correct. So you can take statement A. So let's consider statement B. The sample is acidic. So usually what we consider is, when pH is 7, we consider it neutral. That absolutely neutral. But once the pH reduces, we say it is acidic. But in this case, I am saying it is got to be neutral. Actually, statement B has to be wrong. Why? Statement B is wrong. Because you are going to have same amount of H3O plus and same amount of OH minus. So hydronium ion and the hydroxide ion, both of them are going to have the same amount of concentration that we have. As a result, in pure water, there is no one that is going to make it acidic or basic. Usually, when water has a Kw at room temperature, it will have Kw is equal to 1 into 10 to the power minus 14 mole square decimeter minus 6, right? Mole square decimeter minus 6. Here, if you consider the same thing, here the pH will be 7. So you will say it is neutral. You will say it is neutral because pH is 7. But since pH is 6, you can't say this is acidic. Why? Same amount is there, no? Because here also you will get H3O plus concentration as aqueous concentration as 1 into 10 to the power minus 7. Right? Because you will get the same, you will do the same procedure over here, what I have done here. So the same thing will happen. So you will get 1 into 10 to the power minus 7 mole decimeter minus 3. The same thing will happen here. So according to the argument that most of the students have said, like it can be acidic, but according to my opinion, this statement is wrong. Why? Because here you're going to have the same concentration of H3O plus and OH minus at the same amount. But keep in mind, the concentration value is quite negligible. The concentration that you have found for the H3O plus and OH minus also will be negligible when compared to the water molecules. So therefore you can say that pure water is absolutely neutral. So therefore B statement is actually wrong. B statement is absolutely wrong. Let's see this C statement. What does C statement says? The OH minus concentration is not equal to H plus ion concentration. This is absolutely wrong. Why? The same amount will be distributed here and here. Therefore, the ionic product that when you are writing the ionic product of this water, you will consider the H3O plus and OH minus amount as same. Why? Because you are using pure water. You didn't use any strong electrolyte or weak electrolyte. Strong electrolyte means those who release H plus or OH minus in the aqueous medium completely. They are called strong electrolytes. Weak electrolytes mean those particular substance they partially release H plus and OH minus in their respective media. For example, you can say acetic acid, ammonium hydroxide, right? All those people, they release partially. So that may affect the concentration of H3O plus and OH minus. So you can't say here their concentration cannot be equal. So that's actually absolutely wrong. Here both of their concentrations are same. So this statement is wrong. Why? Since it's pure water, the amount of H3O plus aqueous that you have is going to be equal to OH minus aqueous. This is absolutely wrong. Right? Let's see the D statement. The OH minus concentration is 1 into the power minus 6. Yeah, absolutely. Why? The mole ratio between each of these people are same. So if the mole ratio is same, you can say the mole ratio can be directly proportional to the concentration of the substance that we have. So here you have 1 into 10 to the power minus 6. So that is a concentration of the water H3O plus hydronium ion. So this can be equal to OH minus aqueous. OH minus aqueous. So this is absolutely correct. This is absolutely correct. So therefore D statement is correct. Right? D statement is correct. So we have statement A correct, statement B is wrong, statement C is wrong, statement D is correct. So we have A and D as the correct answer. So the answer that we are going to give is the fourth answer. Right? So fourth answer is the correct one. Right? Hope you guys are clear with what I have explained. Right? The ionic product is the case that we have to be very careful. Here itself most of the students will get mistakes thinking that pH is 6, which means it can be acidic. No, water is actually neutral. Pure water is actually neutral at any situation. Since maybe the temperature of must have been increased, so that the KW must have been increased. Here it's minus 14, it has become minus 12. So this is bigger, which means the temperature of the water is being kept higher than the room temperature. That's what it has been happened. So therefore, you can consider the A and D statements are correct. So therefore, you're going to get the fourth answer. So by the way, we have finished the chemical equation based questions of most of the physical chemistries and all those areas of 2004. We'll meet you in the 2005 paper discussion.